Hello everyone. My name is Nemat Farhadi. First year grad student. Sorry. A first year grad student at Virginia Tech. My today is about observation of ferromagneto-elastic resonance in iron 70 vanadium 30 thin films. Uh, I will start from energy, the problem of energy loss. We've all felt the laptop get hot on our laps when we when we work with a laptop. This heat is wasted energy, and this is the single and the biggest barrier for our electronics to become faster and more efficient. But my question is that what happens, where this wasted energy go in in a magnetic device? This is the question I'm gonna answer today. To understand this, we know that we need to know our key players. First, the spin, which is a tiny spinning bar magnets in magnetic material. In metals, the main path for energy loss is uh, spin electron interaction, which is like a loud roar. But there is another path also. And the player of this path is phonon. Phonon is a very small packet of sound energy in a crystal lattice. A spin can also lose energy by creating phonons. And by creating phonons, uh, but the point is that this path is like is usually drowned out and is like a whispering comparing to spin electron uh, damping, spin electron coupling. So our central question is that can we observe this hidden spin phonon whispering and uh, uh, can we observe this hidden spin phonon whispering? The answer is we might can, but definitely in a quiet room. Which we chose if we choose our a quiet room properly, we can observe this interaction. Our quiet room here is iron 70 vanadium 30, an alloy of 70 atomic percent of iron and 30 atomic percent vanadium. We chose this because it's known for its weak spin electron interaction. Oh, okay, so let's start. I'm gonna talk a little bit about my sample. So to be able to see this subtle whispering, we need our iron vanadium layer to be perfect with low defect crystal structure. So for that, and we need a crystal template for its growth. And our choice is copper. A thin layer of copper forms um, forms in a naturally in ordered surface, and its atomic spacing is well matched with iron vanadium. And there is another problem. Iron vanadium rusts at the moment it touches the air, so we need a particular layer on the top. Our choice is a thin layer of titanium because it's very reactive and can build a side skin as a shield. Uh, and the other thing that we have to consider is that our substrates is either bare silicon or thermally oxidized silicon. And unfortunately, copper doesn't well bond with with its glassy surface. So we need an adhesion layer. Our adhesion layer is again a thin layer of titanium because it's highly reactive and can form a strong chemical glue to our substrate. After making our sample, we need to know how do we do our measurements. We use out-of-plane measurement. Out-of-plane measurement is ferromagnetic resonance spectroscopy. Let me briefly tell you what happens in FMR. The first step is that we place our magnetic sample in a microwave waveguide. Then we apply a an external magnetic field. This external magnetic field makes all spins wobble, but sorry, makes all the spins align with the external magnetic field. But since those all of these spins have angular momentum, they start wobbling around the field direction. And then we uh, apply microwave at a specific frequency, and then we slowly sweep our magnetic field. But at one specific magnetic field, the natural frequency of wobble of spins resonate with the microwave frequency. At this moment, which is ferromagnetic resonance or FMR, spins absorb energy, and the microwave energy is absorbed by spins. So uh, we can plot a graph like this, and the line width of this FMR peak tells us how fast energy can be absorbed by spins. If we do measurement for, we did measurement for uh, 25 nanometer of iron 70 vanadium 30 sample, and we plot a line width for different frequencies, and we got this straight line. This is if we fit this data point by Gilbert damping relation, we will get uh, Gilbert damping constant smaller than 0.003, which is indicating that our iron vanadium is very low damping, and so we can say that our quiet room is ready now. But where is phonon? We talked about phonon, but where is phonon? Uh, the phonon shows up when we do measurement for thicker, do FMR measurement for thicker films. So the plot at the right-hand side is our line width for 120 nanometer film. We observe a very clear and sharp bump. This bump uh, is indicating that there is a new energy loss channel in this magnetic material. So again, we have to ask ourselves as what is this bump? To see what this bump is, to figure out what it is, we measure a line width for different and other thicknesses. Based on our observations, we made an hypothesis. A hypothesis is that our bump is coming from a mechanical uh, mechanical wave. So it's something like standing wave resonance. So the phonon growth is showing up here. But how can we prove that? Are we sure that this is standing wave? So we know that for a standing wave, the frequency of resonance is determined by the size of the cavity, which here is our film thickness. And if you look at our plots, you can see that when we make our film thicker, the bump frequency go systematically to higher and higher frequencies. Furthermore, if you look at this 200 nanometer film, we see three bumps. It's like first, second, and third harmonics of this standing wave. So uh, we can't say that our hypothesis is true. So, and if we make a plot of bump frequency versus inverse of film thickness, we can see that we got a very straight line and a linear relation between frequency and the inverse of thickness. And it's also predicting that for our thinner films like 50 nanometer and 25 nanometer, the bump frequency should be in 28 gigahertz and 56 gigahertz. According to our observation, these two uh, frequencies are out of our measurement range. So now we are convinced that we are dealing with a standing wave. But what is going on here physically? Let's start from the beginning. In our FMR experiments, we said that the microwaves can create can create wobble in the spin. The quantum of this magnetic wave is called magnons. But at the same time, our film can host also mechanical vibrations, which, as we mentioned, is called phonons. The packet energy of this mechanical wave is phonon. But the question here is that how these two separate systems interact, talk to each other. The answer is that they are linked by magneto-elastic coupling. It means that uh, the magnons and the magnetic wobble, it can physically pluck the crystal lattice. So the bump is the ferromagneto-elastic resonance, or FMR. It means that the frequency of magnons is matched with the frequency of the phonons.
Hey, Nemat, you're at
And
about 12 minutes, so if you can maybe start to wrap it.
Oh, okay. So the bump is like a new peak in. I'm about to finish. The bump is like a new channel of losing energy in our sample by transferring energy from magnon to phonons. And there's another thing is that can we turn the resonance on and off? The answer is yes, because if we change our substrate, we can see that the bumps vanish. The bumps vanishes. Why? Because the substrate, when we use silicon oxide has a very has acoustic mismatch with iron vanadium, so it can trap phonons and we can see bumps. But if we replace silicon oxide with bare silicon, there is no acoustic mismatch, so phonons can escape and we see no bump. So in summary, we can say that we found we observed external damping in iron 70 vanadium 30 films that originating from spin phonon interaction. To see the bumps, we need two conditions. The first condition is that FMR frequency should be equal to acoustic wave frequency, and we know that acoustic frequency is inversely proportional to the thickness of our film. And the other condition is that we should use a substrate with acoustic mismatch. Thank you for your time.